let us start this lecture with a thought process. We have taken birth in this earth to use the inner fire for the benefits of mankind without getting burned by it. So, if you recall, in the last lecture we initiate the discussion about the one dimensional combustion wave, and where we have found out the difference between the detonation and deflagration. And today we will continue how to analyze the one dimensional combustion wave. So, as I told that combustion wave will be having certain speed, and with which it will be traveling toward the fuel air mixtures, and it depends on the type of fuel air mixtures and also the equivalence ratio. And in case of deflagration, we have seen that if it is the speed of the combustion wave is subsonic, we call it as a deflagration, and if it is greater than the sonic speed, then we call it as a detonation. And question arises, practically when there will be deflagration, when there will be detonation. For example, if I take a tube mixed with the fuel air mixtures, right. This is fuel and oxidizer mixtures, right, it is being filled. If I ignite it, right, as I told earlier that if this is the igniter, what will happen? This kernel, the ignition kernel will be moving toward that, then will it be a detonation or will it be a deflagration? Right, because it will be moving with a subsonic speed. So, therefore, it will be basically a deflagration. Now, what will happen if I close this portion? This is a close, both are open tube, this is a tube, right, tube is open both the side. If I close and if this is filled with fuel oxidizer and I will ignite it, what will happen? Will the flame will be moving with the same speed, right? Combustion wave will be having certain velocity or certain speed, and it will be always moving towards the fuel and oxidizer. Therefore, we are calling it as a speed because the direction is known, right. So, we can call it as a combustion wave speed, right. Will it be in the same, right? It will be changing, but will it be, why it will be changing? Fuel air mix, this in the beginning it is a 0, there is no movement as such. So, it will not be changing unless it reaches here nearby, it may change because the pressure will be built up in this region. When the flame propagate, it will be propagating, will be moving, right, and then toward that there will be some pressure will develop, right. Will it pressure will develop? No. Why it will develop? Because I have told compression, where it will be? It is a moving, it will not really compression will be taking place. But however, I will do other way around. What I will do? Let us say I will close this side, and this is fuel and oxidizer. Keep in mind that this is stationary mixed, there is no movement as such. I am not talking about that of the movement of the movement of the fuel oxidizer mixture. Okay, it is just stationary mixture. Then what will happen? I will ignite here. This is your igniter, right. What will happen? This is a closed one, closed tube is closed, this tube is closed, right. What will happen? Because this kernel will come and this also will go this side, there might be some mixture, right, and then what will happen, this will be, and this will be burned and this will be unburnt, right. So, that means the temperature will be very higher. As this is closed, the what you call expansion will be taking place of the gas, because temperature is higher. If the temperature is higher and expansion, but it is closed, so what will happen? It will be trying to get compressed, yes or no, right. So, if it is there, then what will happen? It will be trying to basically get compressed. See, you know the adiabatic temperature you have seen, the mixture, let us say 300, if it is fuel methane air, what will be the temperature? 2200 Kelvin into divided by 300, something around more than 6 times it is changing, right. So, therefore, there will be change in the pressure, and then pressure will be acting like a piston, as if there is a piston which is moving the wave. So, it will be moving at a higher velocity, and it happens to be the higher than the speed of sound, right. What will happen? Detonation will occur. That means there will be deflagration to detonation, right, which will be taking place. But this will occur, why? Why does it occur? It occurs because what will happen, there will be a compression. If there is a compression, right, there will be shock formation, and once this is, the shock will be fed by what? By the chemical reactions, right. The shock will be here somewhere and the heat is taking place here, right. There will be shock once it is detonation, right. Then that will be feeding the shock. Are you getting? The velocity will be very high, and then it will be moving, it will lead to the detonation. So, therefore, of course, it is a quite a complex process, but keep in mind that whenever detonation is there, there will be shock, okay, and it will be, shock is fed by what? Fed by the combustion or the heat release, right, which will be much higher speed than that of the whatever the natural or the shock will be there, right. So, now we will be considering and the one dimensional combustion wave, but actually in real situation it need not to be one dimensional, okay. And let us say that we will say this is as a station 1 and I am considering as a, this is station 2 kind of things which we will be discussing, and we will make some assumption for analyzing this thing. What are those? One, consider that we are considering as a steady combustion wave, but in real situation it need not to, because it is coming from the deflagration to detonation. So, therefore, it not, but we are considering it is already developed, only it is moving with a detonation velocity or the speed. So, therefore, we are considering as a steady. The assumptions are steady combustion wave. Keep in mind that when we are analyzing it, we are not considering basically whether it is a deflagration or detonation, we are considering it as a combustion wave. That means, it may be a detonation or it may be a deflagration, that you keep in mind. And we are also considering that the inviscid adiabatic flow, that means no heat, although heat being released, no heat is going out from here, that means Q is 0. But however, heat being generated inside, right, due to what? Due to chemical reaction, right, that we are considering, but no heat is going from the system. If I consider this as a system, you know, if I consider this as a control volume, from this no heat is going out and it is inviscid, that means there is no viscous effect, viscous is not playing an important role. And 3 is the no body forces. either electromagnetic or gravitational, no forces are there, right. But however, when the deflagration detonation which will be occurring in the supernova or some other places, it will be quite complex. Supernova, cosmic phenomena, right. So, there also people are saying it is occurring because of deflagration to detonation, right. So, but here we are not considering those body forces, and the 4 is negligible due for an interdiffusion effect. We are not considering, we may not consider the basically species equation to it. And the ideal gas, right, we are considering the ideal gas, the gas need not to be ideal, right. And 6 is the chemical reaction is being modeled by the just heat release, right. And then we are not considering the species equation, because it is just you are adding some heat, are you getting, instead of chemical reactions. And another thing, we are also assuming as a constant properties, which is not true. That means Cp is a function of temperature, right. So, also the other properties which you are saying is remaining constant. So, we are not, rather we are using the same gamma value, Cp by Cv will be using, but which is not true, because across the combustion wave there will be rise in temperature, change in density, change in pressure, all those things will be taking place, we will be not considering those into account. Okay. So, with this assumption, now what we will have to do, we will have to basically invoke the conservation equation like continuity. What it would be continuity, that means for this one dimensional what you call combustion wave between the station 1 and station 2, if you look at, see this is your station 1 and this station 2, we are considering in between, right. So, what it would be, if I say the rho 1, if I say this is basically rho 1 V 1 P 1 T 1, right, rho 2 V 2 P 2 T 2, right, then we can relate those properties. Rho 1 is the density, V is the velocity, P is the pressure, T is the temperature, right. I can write down then as the rho 1 V 1 is equal to rho 2 V 2 is equal to mass flux, right, rate, this is mass flux rate, right. From the momentum equation, if you look at what it would be, that will be nothing but P 1 plus rho 1 V 1 square is equal to P 2 plus rho 2 V 2 square, because we are not considering the body forces and it is inviscid. So, therefore, those terms are not coming, which is a very simple, and this is similar to what you might have what you call use for analyzing a normal software. Keep in mind that here we are considering as a combustion wave, right, which is one dimensional in nature. So, this type of equation you might have used there. So, energy equation, what it would be? It will be for a ideal gasless. So, therefore, Cp 1 T 1 plus V 1 square divided by 2 plus Q. Q is nothing but your heat release rate, and which is due to the combustion. However, in this case we are saying that it is substituted by the heat, but however we can use also some for calculation purposes we can use that as a from the enthalpy balance kind of thing, is equal to Cp2 T2 plus V2 square divided by 2, right, this is a kinetic term. So, beside this as it is a compressible flow, so we will have to consider equation of states also. For station 1, that will be P 1 is equal to rho 1 R T 1, and for station 2 P 2 is equal to rho 2 R T 2, right. R is your specific gas constant, right. This is your specific gas constant. So, Q is the heat release rate per unit mass, and I can write down this as YI HI FI naught, right, and where YI is the mass fraction of I species and HFI naught is basically heat of formation of I species, right. I can say this is as a equation 1, this I can consider as a equation 2, this is equation 3, I can consider this as a 4 and this is equation 5. So, from equation 2 I can write down, or by using equation 2 we can have P 2 minus P 1 is equal to rho V 1 square minus rho 2 V 2 square. I can write down as rho 1, this would be 1, rho 1 V 1 whole square divided by rho 1 minus rho 2 V 2 whole square divided by rho 2, which is nothing but I can write down by using continuity equation. This is the equation rho 1 V 1 is equal to rho 2 V 2. Then I can write down as mass flux square equal to 1 by rho 1 minus 1 by rho 2. And this equation is basically, you can consider this as a Rayleigh equation, right. I can write down this as rho 1 V 1 square is also equal to rho 2 V 2 square is nothing but P 2 minus P 1 divided by 1 by rho 1 minus rho 2, and this equation is basically known as Rayleigh relation. I will consider this as, okay, let me write down here as a equation number 6. And from by using this equation 6, I can basically derive the relationship for the velocity at station 1 and also the velocity at station 2. Similarly, I can also find out Mach number at station 1 and Mach number at station 2. So, let us that by using equation 6, V 1 square is nothing but your P 2 minus P 1 rho 1 square 1 by rho 1 minus rho 2 P 2 minus P 1 rho 1 I can write down as similarly we can have V2 square as P2 minus P1 rho 2 by rho 1 minus 1. Now, we can express this as basically in terms of Mach number. We know the Mach number is nothing but your M1 square is nothing but your V1 square by C1 square, and C1 square is the speed of sound is equal to C1, which is nothing but your root over gamma RT 1 is equal to root over gamma P1 by rho 1, right. And I can write down, substitute here, I can find out this will be P2 by P1 divided by rho 1, and this will be, I am let me write down here 1 minus rho 1 divided by rho 2 into what it will be, gamma P1 divided by rho 1. So, this rho 1 will be cancel it out. So, I will get as P2 minus P1 divided by, it became, because if I take P1 here, this will be P2 by P1 minus 1 gamma, right, into 1 minus rho 1 divided by rho 2. Similarly, I can, this is basically equation 9. Similarly, we can have M2 square, Mach number at station 2 square is nothing but your 1 minus P1 by P2 gamma rho 2 by rho 1 minus 1. So, now we know, we can relate this pressure ratio and density ratio and gamma to the Mach number, right. In other words, Mach number at both the station can be expressed in terms of pressure ratio, density ratio and gamma. Now, we will be basically deriving expression for the heat release using the energy equation by using equation 3. We can have is nothing but your Cp T2 minus T1 plus V2 square V1 square divided by 2, right. And if you look at the CpT2, right, what it would be, can I not express in terms of pressure? For an ideal gas, we know the Cp T1 is nothing but your, what is Cp? Gamma minus 1 R T1, right, is nothing but a gamma minus 1 P1 by rho 1, right, yes or no. Similarly, I can write down Cp T2 is gamma minus 1 P2 by rho 2. and from equation let me say this is basically equation maybe 10 it would be, okay, 11. So, this is 11. By using equation 2, we can have expression for V2, right, and V1. We can have V1 square is nothing but here P2 minus P1 rho 1 plus rho 2 V2 square divided by rho 1. And similarly, I can write down this as a basically 11, 12, this is 13, this is 14. So, V2 square is nothing but your minus P2 minus P1 rho 2 minus rho 1 V1 square divided by rho 2, this is 15. By using equation 12 to 15 in equation 11, we can have Q is equal to what you call gamma minus 1 into P2 by rho 2 minus P1 by rho 1 then it will be plus half, that is V2 square, right. V2 square will be nothing but your P2 minus P1 by P2 right minus plus rho 1 V1 square divided by rho 2 and minus P2 minus P1 rho 1 minus rho 2 V2 square by rho V1. Okay. Keep in mind that this will be cancel it out, this will be cancel it. Why? As to equation 1, that is continuity, right, because that will cancel it out. So, then finally what you will get? You will get basically Q is equal to gamma minus 1 P2 by rho 2 minus P1 by rho 1. It will be minus half. I will take P2 minus P1 as a common, P2 minus P1, I will get 1 by rho 1 plus 1 by rho 2. This is basically known as the Rankine-Hugoniot relation, which is one of the most important relationship in the explosion and the flame, right, because flame can lead to explosion, right. So, this is a very important relationship, you should we will be using it, and this is 16. With this we will stop over here and we will discuss in the next lecture.